All right, so here we have a situation that's fairly common in reality. You've got things stacked on one another, and you don't push on the bottom thing, you just push on the top thing. All right, and kind of what happens to that, now. Um, so what could happen is, you push on the top thing, and maybe both things move. Okay, together. Maybe they move together like they're a single unit. Okay, boom, just like this. All right. But a lot of times you push on that top one and it's just going to move by itself. Okay. Sometimes you could push on the top one and it'll slide and the bottom will move a little bit, but the top one moves more. Okay. So we've got these like three different possibilities for well, I guess there could be a fourth possibility. You could push it and not move at all. Okay. So we have these different scenarios. We're going to figure out how they're going to play out. Okay. So we're pushing against A with P. All right. So we're pushing on A, and then we've got B down there. Now, they've made this a little bit simpler because there's no friction between B and the bottom. Okay. So that's smooth. All right. So that sort of makes things a lot easier to analyze. Okay. But basically we want to know if we push on the top block, what happens to the other two blocks. Okay. Now we're going to start thinking about this by not even worrying about P for a second. Okay. So what we need to think about is, because P touches A, why does B even move? Why does B even move? Well, let's kind of redraw our scenario just a little bit and think of it this way. So I've got I've got B down here. Okay. B is going to have some friction pushing it here. Okay. Now, right now, we don't know if that's going to be kinetic friction or if it's going to be static friction. So I'm just going to leave it generic. Okay. From block A's perspective, it's got P, of course, but it feels that drag, so to speak. It feels that force back from B, okay, trying to slow it down. Okay, so the blocks experience different things, okay, just like this. So what I want to do is say, well, since it's really the friction that is going to accelerate B, let's play that out. Let's suppose that that was the only thing in this whole scenario, B and some friction. Okay. Now, if we have that as our scenario, then we can write something like this. We can say that friction, okay, is going to be equal to MAB. Okay. So we'll do it like this. Okay. Now then, we got to say, is that going to be kinetic friction or is it going to be static friction? Okay, so we'll sort of like do it like this. Let's say we got two different scenarios. Okay, so if it's static friction, which is equal to MBAB, then that static friction is going to be less than or equal to mu times the normal force between them. Okay. On the other hand, if it's kinetic friction, MBAB, that's just equal to mu times the normal force. There's no inequality sign. There's no greater than sign. Okay. Now, in this scenario, our normal force is just the weight of the top block, 20. Okay. And so we can say that this is mu, and that's going to be static. And this one's kinetic, by the way. Okay. Static, and that's going to be MAG. Okay. Greater than or equal to MBAB. Okay. And so our acceleration then, AB, is going to have to be less than or equal to mu S MAG over MB. Okay. Now we're going to get something similar. I'm going to put a visual distinction in here for the other one. But it's going to be equals mu k mag over mb. Okay. Now, I'm going to give you those numbers here in just a second, but I want you to notice we're in English units here, pounds. Okay. So you've got to be pretty careful when you deal with that. Okay. So that means when I'm dealing with MB, I really need to put 50 pounds divided by 32.2 feet per second squared. Okay, that value right there is my mass for B. MA, I don't have to worry about it because I got the G on there, so that's already 20 pounds. No problem. Okay, so that works out just fine. So be careful when you're doing those. Now, here's how that works out. Okay, if you plug in those numbers, in the one case, AB has to be less than or equal to 5.15 feet per second squared. And in the other case, AB has to be equal to 3.86, well, I don't need any more digits, feet per second squared. Okay? So let's go back to our 4 scenarios with the block. Okay, so scenario number 1 is we push with P, all right, and well, there's no friction with the ground. Okay, so if there's friction with the ground, we've got the 4 scenarios. In this case here, we push with P, okay, and the first scenario is the blocks stay together, okay, and they move as a unit. All right. The second scenario is the top block slides and it has one acceleration value. The bottom block has a different acceleration value. Okay. So if it's sliding, the acceleration of that bottom block is going to be this number right here. Okay. Guaranteed. All right. If they're sticking together, then there's a limit to how much acceleration the static friction can provide. Okay, so what we're going to do now is we're going to say, let's assume they stick together, figure out what that acceleration is, and then compare that acceleration to my 5.15 number, okay, and see what we get. All right, so we'll use blue here. Set up Newton's laws here. And so what I'll have is that P is just equal to MB plus MA times A. Okay, so if they move as a block, you remember there's no friction with the ground, then this is what we got. Okay, very straightforward. Okay, so I'm going to have A is P over MB plus MA. All right. Now with numbers, okay, I'm going to have 6. And then remember, we've got to put block B is 50 over G, 32.2, plus 20 over G, 32.2. Now that number is 2.76 feet per second squared. Okay, so now we can compare. Okay, and the stuck together is smaller than the max that the static friction can provide. Okay, so in our scenario here, yep, if we push with 6 pounds, both blocks are going to move together. Both blocks are going to have 2.76 feet per second squared of acceleration. Okay. Now, let's suppose that this isn't part of that problem, but we're just going to explore a little bit. Okay. And let's suppose that we let P equal to 60. Okay. Then what's going to happen? Okay, well, if it's 60, okay, over here, I would have 60 just like that. Okay, and what that's going to result in is that my acceleration is going to be 10 times as much, 27.6 feet per second squared. Now that number, okay, that's too big. It's bigger than our number down here, which means the static friction cannot hold them together. They're going to slide apart. Okay, then I have to look at them one at a time. All right, one at a time. And so for block A, whoops, for block A, I would have my 60 pounds minus the kinetic friction between the two blocks, MAA, like this. And that's going to give me a certain value, and it happens to be, in that case, AA is 86.9 feet per second squared. Okay. For block B, okay, we already have that answer. It's right there. AB is 3.86 feet per second squared. Okay. So that's our situation there. Okay. Now, kind of what would be a good exercise for you to do would be, how would all of this play out if there was friction with the ground? Okay, if there was some friction with the ground, and that's going to make a huge difference in how all this plays out. And in fact, it's going to be much more likely that the bottom block won't move. Okay, and the top block would just slide across it. Okay, or we might end up getting the bottom block to slide just a little bit. Okay, but kind of think through how might that work. Okay, kind of fun. All right, so this one's got lots of little interesting nuances to it there. But this is the last video in this series. Okay, so you should be well equipped for your homework. All right.